All right, howdy. Let's see what we've got. So I'm going to modify the previous problem in a couple of ways so that I can do conservation of energy instead of just talk about potential energies. The big one, the big change is going to be I'm going to make this guy massless. That's only going to resolve some conflicts regarding collisions and things like that really we don't need to worry about. We don't need to worry about some of the problems that happen if this has a mass. Now we could, but we haven't gotten to collision theory yet. So maybe this would be a good example for collision theory is to give that platform back its 2 pounds of mass or 2 kilograms of mass. But actually, I've already written those problems, and there's not such a problem in the examples. So maybe I'll give a bonus example, since there are fewer examples for this one anyway. So what we do with this one is now we're going to pull this guy down, and we're going to have a stronger, stiffer spring. That's because in the previous example I wanted to show the interaction between the different energy terms. So I wanted a fairly large compression just to show that there was a large compression, right? So it compressed 1/3 of the way down, so the length of the spring was 2/3 of what it originally was. So in this case, we're going to have a stiffer spring so that when it launches, it'll actually have a positive speed and will launch. So that looser spring would not launch in this situation. So then we're going to pull this down, like I said, and then we're going to hold it at this level and then release it. And then this thing's going to come back up here. When it gets to this point, it will launch, and we're going to find that speed v that it's launching at. Okay, so that's why these little posts are here. That's just to make it very clear that when you get to this point, the platform stops because it's hitting those posts, and it's just the box that's flying into the air. Okay, that's going to mean that this length here is going to be important. So we're already here looking at the potential energy from the spring as being sort of parabolic around that point. This is sort of a linear gravitational potential energy, and we might like to use this as zero. So last time we used the base here as our zero, but the gravitational potential energy can use any point as its zero as long as it's close enough to the Earth. So if we use this point as zero instead, then this distance down x, or in case really minus x, is going to give us the potential energy, right? It's going to give us the gravitational potential energy down here as being a negative number, where it's going to be zero here. That's going to be just as good. This is going to let us do some interesting things like separate the kinetic from the potential energies at the same time. But the best thing is it takes this and this number and it makes them the same number, right? Whereas last time we had to convert from one of those numbers to the other one. Makes life just a little bit easier. So, like I said, we're going to use conservation of energy here. We're going to do that to find this speed. Now, we can't, with the tools that were given in Physics 1, especially in algebra-based Physics 1, figure out what that v is. Instead, what we have to do is, we can't do that with the earliest part. We can't do that with forces and kinematics and so forth. You could do it if you had a lot more mathematics. This is perfectly doable with more advanced mathematics. But you don't want to use the more advanced mathematics. You want to use the simplest mathematics possible to get out of this, right? And the simplest mathematics comes from the conservation of energy, because you're not going to have to do any complicated integral that's going to make you cry. So instead, what we're going to do is we're going to use this conservation of energy that we talked about. And that conservation of energy says that the sum of your kinetic your gravitational potential and your spring potential energy, and those are the only ones we have in Physics 1. We don't have an electromagnetic energy, we don't have any nuclear forces or anything like that. These are the only things that we're worried about. In this case, we just have to calculate K, U, G, and S on both sides, and we should be able to find the quantity we want, V. Okay. So let's look at what we have here. So at this initial spot, this is going to be the left-hand side of our conservation of energy equation, we have no speed. This is where we're launching from. So we've pulled this down here, and we're holding it along this line. We're holding it along this line until we release it. Once we release it, it's going to come back up. But right now, it's right at that spot. So that's our initial spot, is down here. It has no speed. That means this kinetic energy, which is the energy of motion, is 0 because there's no motion. Simple enough. So we only have the potential energy due to gravity and the potential energy of the spring to worry about. So that's our left-hand side. That's our initial. And let's go to final over here. Well, what about the kinetic energy there? The kinetic energy at this point, the box is moving as fast as it ever will. So yes, it has kinetic energy, right? And that kinetic energy is 1/2 mv squared. Or we could just say it's K. Probably should, because I have to fill out the rest of these anyway. So then we look at this and we say, well, what's the gravitational potential energy? Well, we're measuring it. This is our reference point. Since it's our reference point, this is UG equals 0. So UG is 0. What about the spring when it's here? Well, we said that this is the equilibrium length of the spring, right? So that means that it has 0 potential energy there. So neither of these show up. So we have UG plus US equals 1/2 mv squared, or K, which probably should have been. So the next part should be to substitute the energies. So the gravitational potential energy is mg times this minus x, because it's down, plus the spring potential energy, which we said before was 1/2 k x squared, or actually minus x squared. And the kinetic energy is still 1/2 mv squared. So now we have all the symbols out there. We have all the definitions for our potential energies and our kinetic energy. We can just start plugging the numbers in we need, because we have all of these numbers except V, which is the one we want. So how about the mass? We said the mass was 5 kilograms. Okay, and we said that the gravitational acceleration is 9.8 meters per second squared. And we said that x was 20 centimeters. That's minus 0.2 meters. All right, what else do we have? We have the spring energy, that's 1/2. K, which is 980 newtons per meter. It's kilograms per second squared. Times minus x squared. Minus x is just x. Minus x squared is x squared, so that's just 0.2 meters squared. That's equal to 1/2 times 5 kilograms times v squared, because we're substituting that mass. Okay, so what are we going to do here? Now, well, now we have to do all this multiplication. So we have a minus sign here, so that's a minus 5 times 9.8 times 0.2. 5 times 0.2 is 1, so that means this is minus 9.8. Can't see that point, joules. And this guy is 1/2 of 980, which is 490, times 0.2 squared, which is 2 over, or 4 over 100. So we have 19.6 divided by 19.6 times 100 divided by 100. Okay, that'll do, because that times 100 divided by 100 is 19.6. So we have 19.6 joules. That's equal to 1/2 times 5, which is 2.5 kilograms, times v squared. We've done that math, so that means, we can say, we'll just figure out what this is equal to here. So this is 19.6 joules minus 9.8 joules. 19.6 is actually double 9.8, so this is just 9.8 joules. Now we have to divide 9.8 by 2.5, so v squared is equal to 3.92 joules. So that means we have to take the square root, so v is equal to 1.97, really close to 2 meters per second. Okay, so that's our answer. This guy is going to be going at 2 meters per second, going upwards at launch. Okay, so that's more or less what I've done. Again, all I've done is set up this conservation of energy equation, which is the initial kinetic energy plus the initial gravitational energy plus the initial spring energy is equal to the final kinetic energy plus the final gravitational energy plus the final spring energy. I went through, first thing I did was I tried to figure out if any of these things were zero at all, right? So the first part is, how many of these things are zero? Well, this initial kinetic energy was zero because the initial kinetic energy is zero because that's where we launched it from. We're launching it from zero. We're letting the spring do all the work for us. So this guy is zero. And we use this as a reference point. So that's why this number here is negative, is because this is a reference point. So this has a negative gravitational potential energy down here. But at this point here, in the final point, it's zero by definition because we're using it as our reference point. So that guy's zero. And this is also the equilibrium position of the spring. Spring potential energies are parabolas, right? So its potential energy looks like that around its equilibrium position, which happens to be right here. So that's going to be zero there as well. So that gave us this equation to solve, which is the final kinetic energy is equal to the initial sum of the initial potential energies. Just because we chose this to be the reference point. So that made things a little bit easier. Otherwise, the gravitational potential energy could be over here. In fact, we could have had two of them. If we wanted to use our reference point from the last problem, we'd have our initial potential energy from that and our final potential energy from that. Okay, so that's basically the trick in the problem. So once you know that, you know everything you need to know about conservation of energy. For now. All right. Thank you very much for listening. I will get this up, and hopefully you will enjoy it as much as I did. I will talk to you next time. Bye now.